Today's video is going to discuss the concept of impedance in electrical circuit analysis. In order to talk about impedance, we also have to cover the terms resistance and reactance. At this point, you should probably be familiar with resistance. Resistance is simply the opposition to current flow, and we're going to rate that in units of ohms. We'll abbreviate that with the Greek letter omega. One thing that will be important for us is to recognize resistance is a real number. So when we use resistance, we use a variable R in formulas. So the most basic formula perhaps is R is equal to V over I. That's Ohm's law. Resistance is equal to voltage divided by current. Resistance will dissipate energy in the form of heat in a circuit. And we have these devices to do that intentionally, to oppose or limit the current flow. And we can also have some unintentional resistance, such as in the wiring or in the traces of a circuit board. So in the case of a wire, the resistance is rho L over A. Rho is the resistivity of the material, L is the length, and A is the cross-sectional area. So the value you get for the resistance of a conductor will be very, very small. And we could actually neglect that when we're doing circuit analysis. Now, getting on to the interesting part, reactance. Reactance is the opposition to current flow in an AC circuit as a result of a capacitor or an inductor. And this occurs because a capacitor stores energy in the form of an electric field, and an inductor stores energy in the form of a magnetic field. So, how do we figure out that opposition to current flow? Well, we come up with a parameter called reactance. And reactance depends upon the size of the capacitor and the frequency of the applied voltage. When we say the size of the capacitor, we mean the amount of energy storage capability of the capacitor, not necessarily the physical size. And we will rate that size of the capacitor, the ability to store charge, in terms of farads. If we're using capacitance in a formula, we use a uppercase C. So uppercase C is epsilon A over D, and that is the area of the plates divided by the distance between the plates multiplied by the permittivity of the dielectric. So when you purchase a capacitor, the manufacturer will tell you the value of the capacitance, and from that we could determine the capacitive reactance, the opposition to current flow. That capacitive reactance is given by X with a subscript C because it's due to a capacitor. So reactance in general is given by an X. X with a subscript C is capacitive reactance. Units for capacitive reactance are ohms, just like resistors. In order to convert from capacitance to capacitive reactance, we use the formula X of C is equal to 1 over 2 pi Fc. Let me repeat that. X of C is equal to 1 over 2 pi Fc. Very, very important formula if you're studying circuit analysis. Once we have the capacitive reactance, you can use that kind of in place of R in Ohm's law, but you have to remember that you're going to get a negative imaginary number. So let's recap. What is an imaginary number? An imaginary number is any number multiplied by the square root of -1. If you're a mathematician, you abbreviate that with a lowercase I. So I is equal to square root of -1. Engineers abbreviate imaginary numbers with a J, lowercase j, presumably not to confuse that with current. So the formula for X of C, 1 over 2 pi Fc. That will be used in place of R in Ohm's law. So we have I is equal to V over minus J X of C, because X of C is a negative imaginary number. X of C is a negative imaginary number, so we put a minus J in front of it whenever we use it in a formula. Inductive reactance will be somewhat similar to capacitive reactance, except of course it's due to an inductor, and the inductor is storing energy in the form of a magnetic field. So we're also going to have reactance due to the size of the inductor and the frequency of the applied voltage. The size of the inductor again, the amount of storage it will hold, the amount of magnetic field that energy it holds, is given in units of henries. And the inductance uses a variable L. So opposition to current flow is given by inductive reactance. And we're going to again use the variable X, but this time we'll put a subscript L there. So it's X of L. And just like capacitive reactance, inductive reactance is also rated in units of ohms. In order to convert from the inductance to the inductive reactance, we use the formula X of L is equal to 2 pi FL. X of L is equal to 2 pi FL, very similar to capacitive reactance, except we don't have the reciprocal. And the other thing you have to remember is, just like capacitive reactance, inductive reactance is an imaginary number. However, inductive reactance is a positive imaginary number, the opposite of what we saw with capacitor. So inductive reactance, positive imaginary number. So whenever we use it in the formula, we put a plus J in front. So X of L is 2 pi FL. Put that in Ohm's law. We have I is equal to V over plus J XL. Now, if we combine these ideas of resistance and reactance, we get a new term called impedance. Impedance is the total opposition to current flow in an AC circuit, and it includes all of these ideas that we just covered. So, units for impedance are ohms again, and we're going to use the variable Z whenever we're using impedance. So now Ohm's law looks like this. V is equal to IZ. V is equal to IZ. Remember, resistance is real. Capacitive reactance and inductive reactance are both imaginary. As a result, when we combine those, we have a real number and an imaginary number. That gives us a complex number. That means impedance is complex. So Z is equal to plus or minus JX. Let's look at an example. Here we have an AC voltage source, 10 angle 0, and a resistor of 1K. So using Ohm's law, I is equal to V over Z. We get 10 angle 0 divided by 1K plus J0. There's no reactance in this circuit. That will give us a current of 10 milliamps angle 0. And the angle is telling us the time difference between the peak of the voltage and the peak of the current. In this case, they are exactly the same. There's zero time difference. Let's look at what happens in the case of capacitor. We have a capacitor of 0.02 microfarads, and we said our voltage source in this case is going to be 5 kilohertz, again at 10 angle 0. So first we have to find the capacitive reactance. 1 over 2 pi FC gives us 1.59 kiloohms. 1.59 kiloohms. Now we could use that in Ohm's law. I is equal to V over Z. So it's 10 angle 0 divided by 0 minus J, 1.59 K. Remember, this is capacitive reactance. We have to put a minus J in front of it. And if you do that calculation, you will get current of 6.29 milliamps, an angle of 90 degrees. 90 degrees again indicates the difference in time between the voltage waveform and the current waveform. In this case, it will be 1/4 of a cycle, 90 over 360. If we have an inductor, we first of all find the inductive reactance, 2 pi FL, works out to 628 ohms. And then we can use that in Ohm's law. V over Z is 10 angle 0, divided by 0 plus J, 628. Inductive reactance, we put the plus J in front of it. Do the arithmetic and you get I is equal to 15.9 milliamps, an angle of minus 90. So 15.9 milliamps, angle minus 90. What happens if we combine, as an example, a resistor and a capacitor? Well, now it gets interesting because now the Z has two parts. First of all, the X is C, which we found previously, 1.59 kiloohms. And now we also have the resistance. So our denominator for Z is the resistance minus J, X of C. So 1K minus J, 1.59K. And now our current is 5.32, an angle of 57.8 milliamps. We can do the same thing with an inductor and a resistor, and the only real difference here is that we're putting a plus J in instead of a minus J. We previously found the X of L as being 628. So 10 angle 0 divided by 1K plus J, 628, gives us a current 8.47 angle minus 32.1 milliamps. Minus 32.1 milliamps. If we have all three components together, the inductor, the resistor, and the capacitor all together, we can just add up the values that we got for the resistance and reactance in order to get the total Z. And in what's called rectangular notation, that's pretty easy. We just add up the real parts and add up the imaginary parts. But when we do that, we have to pay attention to sign. So we have a minus J 1.59K and a plus J 628. So we add those up algebraically and we get a minus J 962. So our total Z is 1K minus J 962. Put that in the denominator. Numerator is a voltage, 10 angle 0. That gives us a current of 7.21 angle 43.9 milliamps. So as you can see, Z is the impedance. It's composed of resistance and reactance. Reactance is imaginary, resistance is real. The sum of those is impedance. It's a complex number. One other thing to point out, what happens if we put capacitors in a DC circuit? Well, as you lower the frequency, the value of X keeps increasing. And you can think of DC as basically a zero frequency. And in the limit, you would get a reactance of infinity. What that means is that for DC, a capacitor is an open circuit. Okay, so if you have a capacitor in a DC circuit and it's there for a long time, it's going to act like an open circuit. Inductors, what you'll find is as the frequency goes down, the reactance goes down. So at a zero frequency, which is kind of like what DC is, we get a value of reactance of 0, and that means that the inductor is a short circuit for DC. In other words, has 0 resistance. So hopefully that gives you a little bit of introduction to what impedance is. Hope you enjoyed it, and thank you for watching. If you want to see more topics related to electrical circuit analysis, check out Mark's Tech Talk YouTube channel.